So we were discussing the properties, how properties changes when you go from normal state to superconducting states. Okay, so two of property already we've seen. Now let us see some more properties, especially thermal properties, how thermal properties changes. Okay, thermal properties means what? Thermal properties. Okay, thermal property means how, suppose how Gibbs free energy changes. Gibbs free energy when you go from superconducting to normal state. Okay, how your entropy changes, entropy. Okay, and how it affects your specific heat. So I'm going to discuss these three quantities. Okay, how these three quantities changes when you go from your superconducting states to or normal state to superconducting states. Okay, so put the heading thermodynamics of superconductors. Okay, so put the heading. Okay, thermodynamics of superconductor. So when you go from normal to how what thermodynamics tells you. Okay, so why I'm applying thermodynamics here, because I told you this is a reversible transition. Okay, आपके पास you have temperature is tool, you increase the temperature below above TC, you become normal. Okay, you reduce the temperature below TC, you become superconductor. So by varying T, you can change the state. That is a reversible phenomena. Similarly, your material is in present in superconducting state. Okay, when T is less than TC, you just apply magnetic field. Okay, equal to SC, and then it will become what? Normal state. You reduce the magnetic field, it will be inside, it will be remain in superconducting state. You increase the magnetic field beyond SC, critical magnetic field, you become normal state. So just by applying magnetic field and temperatures, you can reverse this phenomena. Okay, that's why these states are a reversible state. Okay, now let us check how these properties changes when you go from normal to superconducting state. Okay, so let us, I have a sample, मेरे पास एक sample है, that sample is already in superconducting state. Okay, that means it is below TC. Okay, so I have a sample. Okay, or you can write consider a superconductor. Consider a superconductor. Okay, kept in zero magnetic field, okay, kept below TC. Okay, so I have a superconductor which is placed, whose temperature, who is in superconducting state. Okay, and there is no magnetic field. Okay, now what I am applying? Now I am applying magnetic field. Okay, I have a sample whose temperature is T is less than TC, so it is behaving like a superconductor. Okay, but here H is 0. Now I'm applying some H. Okay, so if I apply some H, what will happen? It will get sample. क्या होगा magnetic field लगाने से?
After HC normal state आ जाएगा.
If any sample is there, I am applying magnetic field. What will happen? It will get magnetized, ना?
Yes, sir.
किसी भी सैंपल को अगर मैं मैग्नेटिक फील्ड में रखूंगा तो क्या होगा? वो मैग्नेटाइज होगा या तो डायरेक्शन ऑफ मैग्नेटिक फील्ड या इन द रिवर्स ऑफ मैग्नेटिक फील्ड. If it is getting magnetized in the direction of magnetic field, then those materials are called your paramagnetic and ferromagnetic material. If it is reversely magnetizing, then it is called diamagnetic material. Okay, so this is superconductor, so it will get magnetized. Okay, so because of this magnetization, what will happen? Its energy will change. Okay, so let me write. Okay, so consider gives free energy, considers the gives free energy of a superconductor. Okay, how gives free energy changes when I am applying magnetic field to a superconductor. Okay, the magnetization, say the magnetization is M. Okay, I'm magnetizing, I'm applying a magnetic field, so material, obviously material will get magnetized, and its magnetization is M. Okay, and magnetic field, okay, magnetic field or induction, okay, magnetic field is H. So the work done in bringing okay a superconductor into a magnetic field. Okay, so the magnetization M and the magnetic field, I'm now bringing the sample in magnetic field, so the work done in bringing a superconductor, okay, from infinite, okay, infinite, I mean here H external 0 to a region where the field is X external, where the field is H external. Okay, so when I'm bringing from it zero magnetic field region to X region, what happens? Okay, give me 1 minute. Okay, so the work done in magnetizing a sample, okay, कैसे लिखते हैं? How do you write work done? So work done in
Sir,
magnetizing,
MDH.
okay, MDH, very good. Okay, so we write MDH from where 0 to H external. You're bringing sample from 0 to H magnetic field. Okay, so magnetic field is doing some work that will store as a gives free energy. Okay, so this work is what? MDH. Okay, now what is the value of this work? How to calculate? Now you know for superconductor M equal to minus H. Can I write like this?
Yes, sir.
Okay, because superconductor is what? It is a superconductor state. That means in that state, when your susceptibility is -1, that is M upon H is -1. That is M equal to minus H. Okay, put the value and solve. Okay, so if you solve this one, this will give you what? W, okay, minus mu naught 0 xt. Okay, put M equal to minus H here. This will give you H dH. Okay, so minus plus. If you solve this one, this will give you xt square. So this much work is done. So your energy will increase by this amount. Okay, so now if I want to write the gives free energy per unit volume of my sample, okay, so gives free energy in a magnetic field, okay, so gives free energy, okay, say temperature T and magnetic field EXT is equal to what? It is equal to gives free energy at temperature T and magnetic field 0. So earlier my sample was in 0 magnetic field. That time its gives free energy is GST 0. T is less than TC. Okay. Now when I'm bringing this in magnetic field, this energy will increase by this amount because this much work will be done. So I can write now my mu naught, okay, h ext square. That means I can say that Gibbs free energy is a quadratic function of magnetic field. Okay. Now similarly, if I take a normal state, okay, when this t is greater than tc, a normal state, and I apply magnetic field, then what will happen? Okay, I hope this what I'm doing is clear to you. Okay, I was having a sample, okay, in superconducting state. Now that sample I'm magnetizing and magnetizing, I'm doing this one. Okay, so I'm getting this much work is done. Okay, so when my
Sir,
हाँ हाँ
sir, one thing, sir, ये work done को sir हम negative क्यों नहीं है sir?
ये ऐसे लिखने का तरीका है इसको. ओके, फॉर्मूला वर्क भी एक तो सिस्टम पे वर्क करना, और सिस्टम एंड व्हाट सिस्टम वर्क्स डज विथ यू. ओके, सो देयर इज ऑलवेज चेंज ऑफ साइन ना.
हाँ सर, जब सिस्टम के
हाँ.
ऊपर वर्क करता है तब नेगेटिव लिखते हैं.
हाँ, दैट इज
ठीक है.
कन्वेंशन है केमिस्ट्री में. केमिस्ट्री पीपल डू डिफरेंटली, वी डू डिफरेंटली. ओके, जनरली वी राइट लाइक दिस. हाँ,
Gibbs free energy ना.
हाँ, गिव्स फ्री एनर्जी. ओके, so GS is what? Gives free energy per unit volume. Okay, so let me write here. Okay, so this is your gives free energy. Gives free energy per energy per unit volume. Okay. Now suppose I have a normal state and I'm applying magnetic field. Okay, so what will happen? Suppose I have a normal state. I have a normal state. Okay, T, which is greater than your TC, and we have external magnetic field. This will be simply equals to Gn T0. Okay, because when you are a normal state, okay, generally normal material, okay, their susceptibilities are very low, so they cannot magnetize. Okay, so they cannot magnetize in appreciably. So once they cannot magnetize in external field, so their Gibbs free energy will also not change. So if it is a normal state, okay, so whether you are in electric, you are in magnetic field or you are without magnetic field, okay, your Gibbs free energy will not change. Okay, so you can write in normal state, okay, the magnetization is very small. The magnetization is very small. Okay, so magnetization is very small. That means the work done is is very small. The work done, or you can write the work done is vanishingly small. So work done is very small. Okay, so you can write in this way this equation. Okay, so say this is my equation number 1. Okay, so this is my equation number 2. Now let me plot this curve. अभी हमारे पास equation तो आ गई है, so I can plot this free energy as a function of magnetic field. Okay, so can I erase this one, this part? Okay, so you can write normal state, the magnetization is very small, so work done is very negligible, so these both are same. Okay, now if I plot a graph, okay, of Gibbs free energy, okay, Gibbs free energy with respect to magnetic field H. Okay, so my superconducting state, okay, that is increasing as this one. Okay, so if I say the difference, this is varying qualitatively. Okay, this is varying like this, is varying like this up to SC पे तो normal state आ जाएगी. Okay, so this is my superconducting state, while this is my Gibbs free energy or superconducting state. Okay, while for normal state, okay, suppose this value is gn with no field. Applying field also will not change the values. Okay, so my Gibbs free energy for normal state, okay, gn is a normal state. It will not change in the presence of magnetic field. Okay, now but at some point they should meet na, when I am applying external magnetic field. Okay, this should equal to a normal state value. Okay, that point we have to consider. हाँ बोलिए. Okay, so now at some point, okay, so at some point both should values match. Okay, so for some H external equal to SC, okay, normal and superconducting Gibbs free energy should match. Okay, Gibbs free energy of Gibbs energy GS and GN should match. Okay, to match कर दो. Okay, so if you match, okay, so suppose I want to write the Gibbs free energy. Okay, so Gibbs free energy I want to write at H equal to SC. So get H equal to SC, my Gibbs free energy of superconductor is given by T SC equal to GST 0 plus half mu SC square. Okay, and the Gibbs free energy of normal state, okay, SC is equal to GN, T equals to 0. Okay, now this both should match. Okay, at T equal to TC, at H is equal to SC, both should match. At H external equal to SC, both should match. So I will write this is equal to what? This is equal to what? G T 0 equal to G N T SC equal to what? This one, GS T 0 plus half mu naught SC square. Can I write like this?
Sir, sir, H external equals to HC, which should match. Is what meaning of this statement?
तो H external to SC हो जाएगा तो क्रिटिकल फील्ड है ना, तो आपका नॉर्मल स्टेट आ जाएगा ना, बाउंड्री पे आ गया, तो आपका सुपरकंडक्टिविटी नॉर्मल हो गया. दोनों की एनर्जी मैच करनी चाहिए. somebody's mic is on. Okay, now we have GNT0 this equation. Okay, so I can write what? So I can write now GN T0 is equal to what? GS T0 equal to what? Half mu naught SC square. Okay, so that means what? When you are, so there's a, so GN, so when your H is less than SC, okay, my GN T0 is greater than GS T0. Can I write like this? Okay, by this equation. Okay, and this equation also you can write like this. If you want, you can write this equation like this: then T0 GS T0 plus half mu naught SC square minus H square. You can write this equation like this also. When you put H equal to SC, this term will become 0, and you have the Gibbs free energy of normal state equal to your Gibbs free energy of your superconducting state. Okay, so when H is less than SC, okay, your Gibbs energy is what? Always greater than your this energy. Okay, now if H is greater than SC, okay, just now I have plotted the graph. Okay, let me draw that plot graph once again, just to write this equation, and let me explain that one. Okay, so please write these equations. No, let me plot this graph again once again. Okay. So what I'm trying to say here. So if I plot this graph once again, my Gibbs free energy versus magnetic field. Okay. So for normal state, this is constant. Okay, this is a normal state. It's a normal state. And normal state, my Gn is constant. Okay, and up to Tc, H is equal to Sc. Okay, this is increasing. Okay, is increasing, meeting some point here. Okay, and they both become equal at H is equal to Sc. Okay, now suppose my if I increase the Sc, okay, in that case what will happen? In that case what will happen? Your Gibbs free energy of superconducting state will increase. If I go beyond, if I go beyond, suppose hypothetically, if I go beyond this one, this is quantitatively increasing with magnetic field. If I'm keep applying magnetic field, it's increasing. So the Gibbs free energy of superconducting state is increasing beyond the Gibbs free energy of normal state. Okay, that's why this state is not stable. The state, if you have two state, out of two state, only that state will be stable for which you have lower Gibbs free energy. Okay, obviously when your H is less than Sc, okay, your Gn is greater than Gs. So your superconductor comes in, your material comes in superconducting states, because this state has a lower Gibbs free energy. Okay, that's why it is in superconducting state. Similarly, if you go beyond Sc, okay, if superconducting state still exists, that will have a more Gibbs free energy compared to normal state, which is not possible. That's why after Sc, your normal state is more stable compared to your superconducting state. Okay, I hope what I told is clear to you. Have you understand this? What I'm saying?
Sir,
Yes,
can you explain one point?
So I'm saying the phase which has lower Gibbs free energy, that is a stable state. Okay, so below Sc, the Gibbs free energy of superconducting state is lower than the Gibbs free energy of normal state. That's why your material goes in different state. That's why your material get transit. That's why your material is in superconducting state, because that has a lower Gibbs free energy. Once you increase the field beyond Sc, okay, so this phase cannot transfer here, because if this phase transfers here, that will have a more Gibbs free energy compared to the normal phase. So whatever phase which has a lesser Gibbs free energy, that will be stable. That will be stable means your material will try to acquire that state. Clear? Okay.
Yes,
So
sir.
that is the only fact you have to remember, that superconducting state has a lower Gibbs free energy compared to normal state. Okay, so superconducting state has lower Gibbs free energy than normal state. Okay, that is these facts are asked in exam, okay, in the form of questions. Okay, which of the following statement is true? So Gibbs free energy superconducting state is lower than the normal state. So we are discussing thermal properties. So first thing we have discussed. Okay, now second thing is entropy. Okay, put the heading entropy. Now, can anyone tell me what is entropy? If I know,
The randomness.
Disorder.
The randomness of system.
Disorder in the system.
okay, so it is a measure of randomness. Okay, so if I have a given Gibbs free energy, how can I calculate the entropy? If I have the equation for Gibbs free energy. Okay, this equation I already have. So if I want to calculate the entropy of normal state and superconducting state, how can I calculate? Okay, so the first order temperature differential of Gibbs free energy is called entropy. Okay, so when you do statics, thermal mechanics, first order transitions, second order transitions, okay, how do you define? You define with the Gibbs free energy, na? If your first order differential is discontinuous, then you first differential of Gibbs free energy is discontinuous, then you have a first order transition. If second order of Gibbs free energy is discontinuous, then you have a second order transition. So your Gibbs entropy you define by the first order differential of Gibbs free energy, that is given by del G upon del T, or since I mentioned the G, so you can write del G upon del T. Okay, or you can write also, this is a per unit volume, so you can write also dg upon dt, whatever you want. Okay, so this is the first order differential with respect to temperature. Okay, entropy. Now you can easily calculate, you have gn, you have gs, you have this relation. Okay, you can calculate entropy. I have a relation gn T0 equal to gs T0, okay, equal to half mu naught SC square. Okay, now just differentiate this equation, so you'll get the entropy of normal state and superconducting state. Okay, so if I differentiate this equation, minus del gn upon del t, okay, minus del gs upon del t, okay, and minus d upon dt of half mu naught SC square. Okay, so this will give me what? Entropy of normal state. This will give me entropy of superconducting state. Now, whether your HC is a function of temperature or not?
Yes, sir. Function of temperature.
Yes, sir. Yes, sir.
Okay, so we told you yesterday na, that this is your SC curve. Okay, this is your SC critical field versus temperature curve. Okay, so this is TC. So your SC critical magnetic field varies with temperature, so it's function of temperature. Okay, just differentiate. Okay, so you differentiate, what will get? Mu naught, you get 2 F naught SC, okay, and DSC upon dt. Okay, so this will give you what? SN will be SS, okay, minus mu naught SC DSC upon dt. Now what interference you can give by this equation? Okay, just look at this equation and tell me which state has a more entropy, normal state or superconducting state.
Superconducting.
Okay, so if I measure this DSC upon dt, this is the positive or negative?
Negative.
Negative, because this, you can see this graph na? This is negative, so this is negative, this become positive. Okay, that means if I take this one, okay, so if you see this graph, this is your negative. Okay, so negative positive, so your SN minus SS is equal to minus mu naught SC DSC upon dt. Since this is negative, you have positive. So if you want to draw now entropy versus temperature, okay, note down these equations, then we will discuss how varies. Okay, so now if I draw the entropy versus temperature graph, okay, below TC, T equal to TC, okay, what will happen? At T equal to TC, what is the value of SC? At T equal to TC, what is the value of SC?
0.
Zero. Very good. So that means at T equal to TC, your SNS is equal to SS. Okay, entropy is same. Okay, here entropy is same. Now if I draw this state of no, at T is equal to 0, entropy will be what? 0. Third law of thermodynamics. Okay. Now this is your entropy of normal state. Okay, this is a linearly decreasing. Why it is linearly decreasing? Can anyone tell why entropy is linearly decreasing? The entropy is 0. I know T is equal to 0. Entropy should be 0. That is third law of thermodynamics. Okay, but it is linearly decreasing. Okay. So if you want to see the variation of entropy with respect to temperature, you always see the variation of specific heat with respect to temperature. Okay. And you know the specific heat variation for normal metal is given by what? CV is given by A T cube plus BT. Okay. And this expression is due to phonon, low temperature phonon. Okay. And this temperature is due to electrons. So specific heat of metal, okay, normal metal, okay, the specific heat of normal metal, okay, I hope this is clear, visible to everyone, is AT cube plus BT. But if you're going very freezing temperature, like I told you, for superconductivity, you require temperature of liquefied helium. When you go up to that much freezing temperature, only the contribution comes in the specific heat due to your this one. Electronic contribution. Okay, so CV is proportional to T here at low temperature. And now if you want to calculate what is S, so S is defined by CV dt. So if you write CV equal to BT, B and TT cancel, it will become simple B. And if once you integrate again, you'll get same. So the dependence of entropy is same, like always the same, like your dependence on this linear case, which is dependence on specific heat. Okay, so since your specific heat is linear, okay, your entropy also is linear. Okay, now this is your normal case. Okay, what about superconducting case? Superconducting case,
Sir,
this,
so specific heat is linear also.
यहाँ से देखो ना, B, if you take low temperature, okay, majority contribution to specific heat comes because of this BT. Your CV is,
okay, sir. Okay,
so CV is BT, na? Okay. So this is linear. Okay. Now if I want to draw here, so normal superconducting state, this should be more. So this will go like this. This will go like this. So this is your SS. Okay. So final conclusion, what I'm trying to say here, is that when your temperature is below TC, okay, the entropy of superconducting state is lesser than entropy of normal state. So these type of questions, they are just asked like a facts. Okay. Then you should know Gibbs energy less in superconducting state. Entropy is less. Entropy is less means what? It is the superconducting state is more ordered state. Okay, compared to entropy का मतलब क्या है? When entropy is less, that means it is a ordered state. Ordered state of what? Ordered state of electrons. Okay, because when you are in normal state, you have a excited electrons in Fermi levels. Okay, you have electrons. When you cool them, okay, those electrons become pairs. They get condensed. So they become boson. They become condensed. So that those material have a higher entropy. Okay, because they become, the randomness is decreased. They become stable. In normal state, they are thermally excited. That's why, and when you become more ordered, your entropy decreases. That's why your superconducting state has a lesser entropy compared to your normal state. Okay, I hope this is clear. Okay, now last thing, let us do specific heat. Put the heading now, specific heat.
Sir, sir, when T is equal to 0 in superconducting state, then is equal to 0 कैसे होगा?
क्या 0 होगा? एंट्रोपी?
हाँ सर,
एंट्रोपी तो हमेशा 0 होती है ना. थर्ड लॉ थर्मोडायनामिक्स यही तो है. T टेंड्स टू 0.
इक्वेशन जो यह हम है, Sn is equal to SS plus mu 0 HC into 2p by tc square, तो t is equal to अगर 0 पुट करेंगे तो Sn is equal to Ss
ये इस इक्वेशन से नहीं पता चलता है, वो तो थर्मोडायनामिक लॉ ही है ना भी आपको तो टी वो तो सिस्टम आपका पूरा ऑर्डर हो जाएगा ना, आप यू गो T0 सब स्टेट विल कंप्लीटली ऑर्डर्ड, ओके, नो रैंडमनेस, एंट्रोपी 0, okay. Now put the heading specific heat, okay. We'll come these points again, okay, and we'll discuss this BCS theory, all those things, okay. So now put the heading specific heat. अभी मैं सिर्फ बता रहा हूँ कि how they vary it, okay. We'll go some more detail about these things, okay. So specific heat. Now how do we define specific heat? Anyone? How to calculate specific heat?
Sir, entropy से calculate हो जाएगा.
Okay. So we know this is dq upon dt, constant volume, okay. Constant. And we can also write this is as a ds upon dt also.
ds by dt.
Okay. So ds upon dt volume, okay. Just differentiate this equation. So dsn upon dt multiplied by temperature minus t dss upon dt, okay. Now differentiate this equation, okay. I'm differentiating this equation, okay, this equation. So this will give me what? Mu naught d upon dt of sc and dsc upon dt, okay. So when I differentiate this equation, okay, this equation will give me what? This is what? Specific heat of normal state, okay. This is specific heat of superconducting state, okay, CSCN, okay. And this is what? Minus mu naught. If you differentiate this one, this will give you if you keep SC as it is, it will give you d2 SC upon dt square. And otherwise, if you like this, if you leave this one and this one, then you will get d SC upon dt ka square. Okay. Now let us discuss the temperature variation of entropies. Okay. Now I hope this you have written this equation.
1 minute, 1 minute.
Okay. So I'm erasing this one. Okay. So if you erase this one, okay. Now you can write, suppose at t is equal to tc, you have sc equals to 0. So cn minus cs will be what? At t equal to tc, you will have cn minus cs, sc 0. That will be, you can put this term 0. So it will be what? Simply mu naught dsc upon dt square. Okay. Now dsc upon dt is negative. So negative square positive. That means cn minus cs, okay, is negative. That means what? cs is equal to cn. Now here the entropy of superconducting state is higher than normal state. That means there is a discontinuity. Okay. How? Now suppose if I draw the specific heat variation, if this is specific heat variation with temperature, okay, if I see the transition at t is equal to tc, and you know at lower temperature your normal state specific heat proportional to t. Okay, but your superconducting state at T equal to TC do not have a same value like your normal state. This is Cn. It has discontinuity. It is very higher values, okay, compared to this one. It will start somewhere here. That means now that is a discontinuity, okay. And so this is the at T is equal to TC, okay. If I want to see the behavior at T tends to 0, okay, so now this is at T equal to TC. Now if I want to see T less than TC, and most importantly when T tends to 0, okay, so near freezing temperature, what is the behavior? Okay, so if I want to see if T is equal to tends to 0, what I can write? Shall I erase this one?
So just 1 minute.
Sir,
Huh.
sir, this last statement, sir, shape blocked line. What if?
So so from here we are seeing at transition temperature there is a discontinuity. Both CS and CN are not matching. Okay, both CN are not matching. Okay, CN का कुछ value है पर superconductivity का TC पे value measure कर रहे हैं. Okay, when we are doing reverse, then this value is very high. Okay, so there is a discontinuity. There is jump. Okay. Now I want to write near T tends to 0 condition. What is T tends to 0 condition? What is happening? T tends to 0 condition. What is happening? So if you see this equation, okay, if T tends to 0, then what will happen? Okay, if T tends to 0, this is your graph. Okay, this is your graph. What? SC by T is a TC. So if you see close to T tends to 0, this curve is what? Parallel. तो उसका slope कितना है? What is slope of this graph?
0.
0.
Okay, so the slope of graph is 0 at T is equal to 0. So you can write at T tends to 0, your DSC by DT is equal to 0. Okay, put this value here. So what you'll get? So you will get when T tends to 0, you'll get Cn minus Cs is equal to, this term becomes 0. You get minus mu naught Sc d2 Sc upon dt square. Okay. So this term is what? Cn minus Cs. This is a negative. Mu Sc. This term is negative. Okay. This term is negative. This term is negative. This term is negative. So total difference will what come? Positive. Okay. So this term is negative. This negative total term positive. That means your normal near T tends to 0, your normal state has a more specific heat compared to superconducting state. Okay. So that means this is variation is like this. Okay. So specific heat variation of your superconducting state, it's exponentially decreasing, and that is a very important result. Okay, why it is so? So in normal metal we give Cv is equal to AT cube plus Bt. Okay, but at low temperature your specific heat do not vary like a normal metal for superconductor. So for superconductor, what we can write? For superconductor, the equation changes. Okay, so for superconductor, the phonon contribution is same. T cube contribution is due to phonon, that is same. But if you want to write Cv, that you can write AT cube plus B, and there will come an exponential term, exponential minus delta KBT and whenever there is an exponential term, okay, here delta is energy difference, okay, related with the band gap. We'll discuss what is that band gap. Okay, and whenever there is an exponential term, what does it suggest? like your Maxwell-Boltzmann statics. Okay, there is an exponential term, isn't it? If you write your Maxwell-Boltzmann equation, okay, how do you write your most Maxwell-Boltzmann equation? N0 exponential E by kt, delta E by kt. So whenever there is an exponential term, that means it suggests there is a gap. Okay, so when we measure experimentally the specific heat of your superconductor, it shows exponential variation with temperature, which is also an indication that there is a must be some gap, okay, between a normal state and a superconductive state. Because when we are giving temperature, because of this temperature, again you are getting normal behavior. Okay, that means whatever electrons are there in super electron state, that going, they thermally get getting excited, and they're becoming normal. Okay, so that means there is some gap. Okay, so that gap, superconducting gap, which is suggested by some experimental measurement like specific heat, and there are other measurement also. Okay, that experimentally, that theoretically, the value of that band gap is given by the BCS theory. Okay, that I'm going to discuss tomorrow. Okay, so what I'm saying here, that your specific heat is a discontinuous at T equal Tc. Okay, at T equal Tc, specific heat of superconducting state is more than normal state, and near T equal to 0, the normal state has a more specific heat. That fact you should remember. They may ask in exam. Okay, so this
what
was,
is the last you
Sir.
explain once?
yes.
So please repeat what you said in the last.
I told the specific heat of superconducting state at T equal to Tc is higher than the normal state specific heat. Okay, and the specific heat at T is equal to 0, close to T is equal to 0, the normal state has higher specific heat than your superconducting state. Okay, यहाँ ग्राफ से पता चल रहा है ना, ये ऊपर है, ये नीचे है, यहाँ पर क्या है, T और TC पे ये ऊपर है, ये नीचे है. So that's how it varies. Okay, so this is the facts. Okay, now we'll discuss.
सर ये
हाँ बोलिए.
कांस्टेंट क्यों ऊपर जा रहा है सर? मतलब इनफाइनाइट
T
इक्वल टू टीसी में
वो इनफाइनाइट वो डिसकंटिन्यूटी शो करने के लिए है. ठीक है,
अच्छा,
कोई कहीं वैल्यू होगा डिसकंटिन्यूटी शो करने के लिए, कंपेयर टू इसकी काफी हाई वैल्यू होती है, सडनली चेंज होता है. ओके, डिसकंटिन्यूटी शो करने के लिए. ओके, सो दिस वाज योर 3 थर्मल प्रॉपर्टी डिस्कस. गिव्स फ्री एनर्जी गेट्स. हाँ बोलिए.
Sir, in this CV equals to AT plus B exponential, how this equation? Sir?
So you're getting exponential variation, na? See, this is a linear curve hai.
Yes, sir.
This is linear curve hai. Here you getting exponential curve hai. So from there we are suggesting, so that is exponential dependence is there, or specific heat. Okay, with
means from graph we are interpreting.
Yes. Okay, theoretically also we can show. Okay, so this is your thermal properties. Now you have to do one homework. Okay, now we have seen that superconducting transitions. So you tell me whether this transition is first order or second order. Okay, so what I'm giving you homework. Okay, so find out. Okay, find out. Okay, the transition from normal state to superconducting state is first order transition, is whether first order transition or second order transition. Okay, in two cases, with when magnetic field is 0, when magnetic field is 0, when magnetic field is present. Okay, in presence of magnetic field, in absence and presence of magnetic field, in presence of magnetic field. So we have a transition. Okay, the transition, okay, can be first order or second order. So in both cases, when we are applying magnetic field, in that case, that you have to show me the nature of the transition, and when we are not applying magnetic field, in that case, you have to tell me the nature of transition. So you, whatever equation we have written here, by seeing those equations, you can interpret it. Okay, because you know, if dg by dt is discontinuous, then it is first order. If d2g by dt is discontinuous, then it is second order. Now you have to check ki whether first order differential is discontinuous or second order differential discontinuous in both the cases. And from there you can say whether which one is a first order transition and which is a second order transition. I hope my question is clear to you. Okay, so I'm stopping here. We'll meet tomorrow. Now we have done 3 classes. Okay, so it's time to we do solve some problem also. Okay, so tomorrow we'll solve some problems which came in previous year questions and some other interesting problems. Okay, which will give us most depth insight of this theory of superconductors. Okay, so I'm stopping here. Any question?
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.